Okay, let me hide the floating controls. And why don't we jump right in? Before we do so, the usual administrative bits, the reading has not changed. And after today, just 2 more weeks, 6 class meetings, including labs left for this class. I will start putting the exam date, which is May, I think it's 5th, from 10:30 to 12:30 for the first time. I didn't pull an 8 o'clock slot, so that's kind of nice. That being the case, the department is also continuing fortunate to be able to be growing, I should say. And on Tuesday, we have a faculty candidate for a teaching position who will be coming in to give a teaching talk, and that will be at 3 o'clock in Sackler Sciences Center, room 121. If you have it in your schedule, I encourage you to come see the talk. Let me mute my thing here. To come see the talk, it will be on a type of solution approach, algorithmic solution approach called dynamic programming. And it will be Ryan Patrick, who is a PhD student in education, who has a master's in computer science and a bachelor's in computer science. And he is enterprising to vie for the position of teaching assistant professor. So the student voice is very important to us. So please come by to chat. And if you are a computer science, I think also or data science major, an invitation was extended for you to come and have lunch with the candidate. I just can't remember when that is. I think it's at noon. Okay. So please, if it fits in your schedule, please do consider attending that. Okay. Any questions? Does that make sense? Yeah. Everyone, Monday morning, bright-eyed and ready to go. Yeah. Okay. In some schools, they kind of have you stand and stretch and stuff, but I won't do that. All right. So why don't we hop right in? When we last left off, to jog your memory, talked about the so-called anatomy of a learner. And for this, we outlined the various components of a learner or learning algorithm. And the purpose of this viewpoint is to prove certain facts and discuss about the so-called physics of learning, all the different choices that you have, and how they impact various capabilities of the learner. Because at the end of the day, what you're interested in is for what you quote unquote learn to apply well to new examples that your algorithm, your system, your model has not seen. And so I won't go over those components. We talked about an example of learning, the so-called credit approval problem. And with this, you input data, a vector representation of each customer. And that information is called from the application. All sorts of variables that are measured collectively represent a particular instance of a customer. And so the idea then is to automate this idea of the credit approval process. So you input into a system and you either get an approval or a denial. And of course, with any sort of system, it's really important to consider the ethical points surrounding your system. The data certainly is very, very important because if you give it bad data, and bad can mean many things, you're going to get bad performance out of sample on your resulting system. But also from an organizational practice standpoint, when things are critical, you treat these mechanized processes as assistants and not having the final say. You always use it as a recommender. You should do this, you should do that, but you let the human being in the organization make that final call for something as serious as mortgage. Because the primary way for most people in the United States for their families to accumulate wealth is through the acquisition of real estate and the intergenerational transfer of assets from one generation to another. Okay, any questions about this? Jar your memories. And then we talked about this idea of representing our vector instantiations for our historical data, our so-called in-sample points. We represent them as points that we plot in some space, or in this case, the Cartesian plane. Why is it 2 dimensions? Because it's easy to talk about it on a screen. But when you plot your data points, this vector representation each one of the tick marks along each of the axes represents a level for each one of the variables, collectively representing an individual. So in this case, graphically, a point represents one of those vector instantiations and therefore one of the customers. Now, it's very typical for the number of dimensions or the dimensionality of your feature space to number in the hundreds and sometimes in the thousands, right? So note that it's not just always 2 or 3 dimensions. It's often the case. It's many more dimensions. And so this so-called point cloud in feature space represents this plotting, if you will, of all of your in-sample points, your historical data. And so these would be all of the historical records representing all of the customers who've come into the bank, okay? Now, the coloring here is more for visualization purposes. And in this scheme, we said the green points are those ground truth points whose labels are approval. And because remember, this data consists of 2 things: the vector instantiation representing the customers, each customer. I'm sort of paranoid about the sound. Yeah, all right, I did turn on the sound microphone. The coloring represents the so-called class label, the ground truth label, assigned by the target function to each one of your in-sample points. And so in our consideration for this discussion, we're going to assume we only have 2 labels: a so-called positive label, approved in this case, or in this application, and a negative label, denied. And so all of those customers who were approved for the mortgage or the loan, they're colored here in green in our point cloud in feature space. And all of those who were denied a mortgage, they're colored in red in our feature space, those red points. Now, sometimes when you look at certain other ways of representing this, you read about it online or in literature, in publications, textbooks, and so forth. Sometimes instead of coloring green, they'll use a little plus sign for the positive points, and they'll use a minus sign for the negative points, just to make you aware of that when you look at things online. And so now, once you visualize your data, and certainly if your data is in more than 2 or 3 dimensions, you're going to visualize it 2 or 3 dimensions at a time, right? So you just have to choose which ones are important. And if time permits, we'll talk about feature selection and actual algorithms and considerations for which ones you look at or deem as important, and ways of manipulating it to synthesize features in a lower ranked dimension. But that being the case, when we see this point cloud in feature space, we now have to think about what our hypothesis set is. We're going to make an educated guess, and that guess is informed by the geometry of this space. And if we look at it, well, one of our goals is to use as simple of a function as possible, family of functions over which our learning algorithm will search in order to find this notion of a best hypothesis. And we said this idea of a best hypothesis is dependent upon an error function, and you have control over that error function. I'll just give away part of the answer. Things you have control of, what's left you don't have control of for other stuff. But nonetheless, you have your error function, and now we're going to enterprise in our hypothesis. We're going to say, all right, well, it looks like a straight line would be a good way to mimic the labeling of the target function. Because if we were able to find a line that cuts across feature space, where I'm pointing out here diagonally across, that line will separate the red points from the green points. And we have a way computationally of computing what side of the line you're on. Okay, any questions? Does that make sense? Jar your memory? All right. And so, why don't we continue forward? The target function provides us with the ground truth labels on the in-sample points. And one of the things we can think of this as this target function dividing or chopping up feature space into 2 parts. One part that's sliced, if you were to draw a line, kind of like taking a straight knife and just cutting across feature space. One partition, if we were to partition it into 2 pieces, would be the red partition. All the points in that part of feature space are denials. And the other slice would be all of those points that are green, they're approved, okay? And so you can also think of this function as something called a decision boundary. That function, drawn in feature space, is this seam that decides whether or not some individual represented as a data point is an approval or a denial. And so in this case, we see that the points on this side, we'll call that the negative side of the line, are denials. And the points on the positive side of the line, the other side of the line, are going to be approvals. And so I've drawn or tried to draw a straight line, but this function doesn't have to be a straight line. It can be some arbitrary polynomial. So if you had a degree 2 polynomial, well, that's just a parabola of some sort. You could have a degree 100 polynomial. That's going to be some weird, funky, wiggly line, right? And so the idea then is trying to select a family of these hypotheses, these functions that we're going to use as a decision boundary. Does that make sense? Any questions? All right. And so you select a family of functions to stand as your decision boundary, and you hope that the function from within that family of functions will partition feature space consistent with the ground truth labeling of this unknown target function. Now, of course, you don't know what the target function is going to do in every part of feature space. You only know what it's going to do for those data points that it gives you. And the hope is that what you learn about the best positioning of your decision boundary will apply well out of sample to new data points that you don't yet or haven't yet seen. Does that make sense? Any questions? All right. And so let's think about a line. And a line on the plane is a type of linear decision boundary. And going back to, I can't remember when they first teach this, equation of a line, y equals mx plus b. If we were to call the horizontal axis the x-axis and the vertical axis the y-axis. And so for an equation of a line, we have two parameters. What are those parameters? Get you speaking more. Yes? Slope and y-intercept. So slope m and y-intercept b. So you notice this line, you can make it go higher or lower. You can move the line, select a different type of line, or you can tip that line more steeply or less steeply by changing the slope parameter. And so for this function, we have two parameters. And every choice of our slope m and our y-intercept b is going to give you a different line within this family of functions we're calling lines on the plane or in the plane. Now, of course, the more that your model can move, I'll call it wiggle, the more parameters you have. A parabola has more parameters than a line. A degree 10 polynomial has all of those 11 many coefficients defining how it wiggles or how it moves. And so the model, the simpler the model, the hypothesis set, the family of functions, the less it'll move. And the idea, and I won't talk about the theory and the physics, is that you want to choose as simple a family of functions as possible with fewer parameters. Okay. If you want to know why, well, take my machine learning course if you ever teach it, or I'm happy to chat with you about those aspects of the physics of learning. All right. So we have two parameters, the slope m and the y-intercept. And each choice of slope and y-intercept determines a different particular line within this family of lines. So going back to our anatomy of a learner, you have your hypothesis set, script H, and these are lines on the plane. And within this, you can have a selection that represents the slope m and the y-intercept b. And so for each choice of a particular line, we call that a working hypothesis. And just to be consistent with the notation, we have little h, and little h, our working hypothesis, is one particular line out of the family of lines on the plane. And so our learning algorithm's job is to search somehow, which we haven't filled in yet, through those lines on the plane for a particular line that agrees as much as possible with the ground truth labeling, approval or denial, with this agrees with the unknown target function. Does that make sense? Any questions? Yes. The decision boundary is a specific line, but you search for it within that family of lines. But you don't know yet which one. All you can do is measure the error to say this particular choice minimizes the error. And there might be more than one. Okay. Any questions? Other questions? No? All right. And so we have our slope and our y-intercept. So let's visualize what our hypothesis set might look like. Now, in our hypothesis set, and this is the best way I could think of visualizing it, we have a choice for M and B. And so each point within this particular hypothesis set, our family of lines on the plane, is going to represent a particular slope and y-intercept. And so we're going to start random initialization, and we're going to uniform at random, select a value for a slope and our y-intercept, the starting or initial hypothesis, working hypothesis, selected from our family of hypotheses. Now, of course, initialization is important. For some cases, you initialize to 0, all of the parameters from your family. Other times, you initialize to something that's non-zero. And so that initialization can impact the amount of time it takes to converge or arrive upon or find some working hypothesis that most closely agrees with the labeling action of the unknown target function. Now, I call it a working hypothesis because one of the things you're going to do is for each choice of a particular function within your family, you're going to test it. You're going to measure its error. And then the question you're asking is, can I improve upon this error? Can I drive it to 0 or as close to 0 as I could possibly get it? Okay. Does that make sense? Any questions? No? So this particular line, if we look at the partition and we said, okay, well, if everything below the line on the negative side going down that way to the right, if everything on the negative side of the line is the working hypothesis guess about those people who were denied, and everything in this direction above the line, let me mark that. So this is going to be the approval side of the line, and this is going to be the deny side of the line. So with that particular working hypothesis, it makes some mistakes. It disagrees with the labeling action of the ground truth target function. So we see here ground truth, these 3 individuals, they were denied, but our working hypothesis said they were approved. So that's an error. Likewise, it said denial. Well, it got these correct, the denials, because ground truth, the labeling action of the unknown target function, says they were denied for a mortgage. But these, ground truth, were approved for a mortgage, right? So that's also an error. So in our error function, what we do, each time we select a working hypothesis, we evaluate our error, so-called in-sample error, and then we enterprise to search or find another hypothesis that can lead to an improvement, a reduction on that in-sample error. Does that make sense? Any questions? No? All right. And so now this 1.5, 1 comma 5 is not a very good line. And so one of the techniques for search is that we're going to find some other line within some neighborhood or distance around the current working hypothesis. Okay, so what if we tried this next one? We have slope of negative 0.5 and a y-intercept of 15. Oh, wait a minute. That coincides directly, all right? So if this line in particular had maybe the deny side is over here and the approval side of the line is over here, then it agrees perfectly with the labeling action of the unknown target function. Now, of course, how you do this is you project the points, vector projection of the points onto the line. And when you project them, either they project on the negative side or they project on the positive side. So mathematically, that's how you do it. And it's just an implementation of that. But at the end of the day, we're counting the number of errors that it makes relative to the ground truth target function's labeling action. Does that make sense? Any questions? And so essentially, you're going to wander a path in your family of hypothesis, in your hypothesis set, and you're going to try, you start out with maybe this one, maybe you're going to try another one, you're going to try another one, search in the vicinity for another one, and you're going to wander some twisty, turny path until ultimately you get to a working hypothesis that we're going to call G, our final best hypothesis. Does that make sense? All right. Now, this sequence of working hypotheses is called a regularization sequence. And one of the physics of machine learning is that you want a regularization sequence, a path of working hypotheses in your family, your hypothesis set. You want it to be smooth because smooth paths generally tend to be better converging final best hypotheses. Okay. Any questions? So here you can imagine if we traced a bunch of working hypotheses over time in a number of rounds on some windy path, it might be the first line, the next line, another line, another line, another line that's tried. Okay. Does that make sense? Okay. And so your learning algorithm then searches for within your family for that working hypothesis that most closely coincides with the labeling action of the unknown target function. Okay, and this is what learning is. Okay. And so once the search terminates, we hope that the line will work well with new data points. And that's called out of sample error or generalization. We want to find functions that generalize well out of sample. Now, suppose then a new customer walks into the bank, and that's going to be this yellow dot here. And so you apply the same process for turning that customer data into a vector of the same size as the historical data. So this person's going to fill out the same application. You're going to extract the annual salary. You're going to extract the years of residence. And then you're going to plot this point somewhere in feature space, wherever it belongs. So now you take your final best hypothesis and you apply it. And it either says, okay, this new person is either approved if it projects on the positive side of the line, or denied if it projects on the negative side of the line. So essentially, what this final best hypothesis is doing, it's predicting what the labeling should be for that out of sample point, that new customer that has never been seen before, based on what it knows trend-wise about where in feature space these values of salary and years in residence should be in order to say this person qualifies for the loan. Does that make sense? Any questions? No? All right. And so it works well with brand new data, means it generalizes well, and that's the whole goal. So what do we need for all of this to work? We need data, okay, and we need a representation for this data. That representation is in vector form. It has to be in vector form. And it gets interesting when you deal with complex data like images or sound. With sound, you're using something called wavelet transform. It's a way of encoding both frequencies, collections of frequencies, and how they occur in time, which is exactly what music is, right? So again, like many of the problems that we talked about throughout the semester, you have to understand and spend about 60% of your time dealing with learning the domain and looking at the data, right? All of the pathologies associated with the data. Any questions? No? And so we need a data representation. We need a hypothesis set. And that choice of hypothesis set, this family of functions, is informed by what you know about the geometry of the data. You also need an algorithm to search through your space of hypotheses for that working hypothesis, your final best hypothesis that most closely coincides with the labeling action of the unknown target function. You also need an error function, a way to quantify how well you're doing, how closely a particular working hypothesis coincides with the unknown target function. Does that make sense? All right. And so there are various approaches or categories, flavors of learning, and we can't possibly address all of them here. But this is just to give you a high level understanding of different ways people think about this. And so the so-called supervised learning problem is what I just showed you. With supervised learning, you have your vector instantiation representing your data, but you also have that ground truth label, and that's the Y value. In the case of the credit approval problem, the Y value is just a set of size 2. We have the approval and the denial. You can absolutely have more than just two labelings. You can have arbitrary k-many labelings. You can actually synthesize that from two-way labelings. Okay. And you have the supervision signal. You're given ground truth, what's going to happen. And what you're trying to arrive upon is what function of the vector information do you need, a line, a degree 10 polynomial, what function you need in order to predict or output the appropriate label, right? So it's called supervised learning for that reason, because you're given this ground truth label, a so-called supervision function that drives your choice of hypothesis from your hypothesis set. And so the linear classifier, what I showed you, is a line on the plane, but you can scale that arbitrarily in dimension. It's called a hyperplane when you're dealing with more than 3 dimensions. And so it's called a line when it's in 2 dimensions. It's a plane in 3 dimensions. And in the case of 3 dimensions, what you're changing when you change these parameters is both the orientation about X, Y, and Z, as well as the location in X, Y, and Z. And when you go to more than 3 dimensions, our hyperplane, again, it just has a set of coefficients, and you're searching for that collection of coefficients such that the working hypothesis most closely coincides with the labeling action of the unknown target function. And so in this sort of example, imagine if you had a vending machine and you know enough now to implement a vending machine, maybe not the circuit part, but take IoT class and you'll get all that. Imagine you have a vending machine and you're going to measure coins. I know people don't use coins anymore, but humor me. And each coin has a size and it has a weight. Okay. So you have, for example, a dime here. If we look at this blue point cloud, we have its projection along the horizontal axis. A dime has the physically smallest size, and it also has the physically smallest mass, the smallest weight. And then we have a penny. Penny's a little bit bigger, has a bigger size and bigger weight. And you'll notice here, every coin, even though they stamp them out, they're a little bit variable in their size and their weight. Some pennies might be a tiny bit smaller than others. Some might be a tiny bit bigger. And if you weigh a lot of pennies with an accurate scale, you'll notice that there's some variability. And so for each coin denomination, we get some variability. And when we plot them by their feature representation in terms of size and mass, we're going to get a point cloud associated with each one of our coin denominations. Does that make sense? All right. And so, of course, nickels are bigger and heavier, and quarters are biggest and the heaviest. So now what we could do is train a bunch of lines on the plane, linear classifier, and these classifiers can be used to detect whether you are a dime or not a dime, a penny or not a penny, a quarter or not a quarter. So you can put a set of these classifiers together and use them to describe complex concepts, identifying, in this example, one of 4 different coin denominations. Does that make sense? But again, this is a supervised learning problem. And with the supervised learning problem, you're given the supervision, all of the labels, yes, this is a quarter, this is not a quarter, this is a dime, this is not a dime. And you're training each of these linear classifiers you're using together. So then once you get your final best hypotheses for each one of these lines, for these denomination classifiers, you then take your final best hypothesis weights, and then you get a computer vision system that's going to look at the size of the coin, and then you're going to measure the weight of the coin, and then you're going to apply that classifier to new coins that come through the coin slot. Okay, and this would be a great semester capstone project, right? But it brings in some aspects of computer vision, which is a specialized study about how you represent image content from cameras. Okay, any questions? So again, the supervised learning is like the credit application, but you can then take these linear classifiers, put them together, and use it to make K-way labeling decisions. Okay, so then we have the other kind. This is called unsupervised learning. With unsupervised learning, you're given your vector instantiation representing each of your data points, your inputs, but you're not given the ground truth label. There is no ground truth target function out there labeling for you. So what are you going to do? How are you going to learn things about your data? Okay. Well, the only thing you can do is examine something about the values of these features. And so certainly this is a depiction of the same coin classification problem, but now we're going to remove the labels. And you notice there's no coloring here. It all just looks like data. So if that's the case, the most you can do is now compare the sizes and compare the masses to try to group them together, so-called clustering. And so clustering, when we talk about unsupervised learning, you're given the data and your algorithm attempts to associate your data points together based on some analysis or statistic over the feature values. Does that make sense? Any questions? No? Okay. And so let's take a look at a specific learning algorithm for the supervised learning case. And this is called the perceptron learning algorithm, or PLA. Now, this dates back to the 50s, and it was an attempt to try to understand what happens with neurons, right? That's where it lends its history. I think it was 1956 at Dartmouth University. AI sort of formally, artificial intelligence formally started as a discipline. So let's define all of the attributes that you would call from a mortgage application. And rather than talking about 2 dimensions, let's extend this to an arbitrary D dimensions. And so the first variable might be the age of the applicant. The next variable might be a category, maybe it's the like gender or whatever for the candidate, and then for the applicant. And then let's say the next dimension might measure the annual salary, and we have years of residence, all sorts of pieces of information. But you collect them together in vector form, and that vector instantiation represents that unique customer through his or her mortgage application. Now, for each one of these measurements, these variables in our vector, we're going to have a weight for our linear function. So when we talked about slope and y-intercept, they're just real valued weights that represent coefficients for that particular linear model, excuse me, the line on the plane. Let's also introduce a threshold. And that threshold we're going to call T. And that threshold is going to represent, excuse me, is going to represent a minimum score that someone must achieve by taking a weighted sum of each attribute times each one of these weights. And it's sum them together. And this T is going to be a real value threshold that weighted sum must achieve. So we take x1 times w1, add that to x2 times wt, all the way through xd times wd. We add up all those weighted sums, we sum them together, and then we compare it against a threshold. Does that make sense? Any questions? Okay. So in our scheme, we're going to take our weighted sum here. So we have the sum for I goes from 1 to d of our wi xi, and that's going to give us a value. And if that value is greater than our threshold T, our score, we're going to approve that person for credit. If that person is less than our threshold T, we're going to deny that person for credit. Now, you might be thinking, what happens if they're equal to T? You have to make a decision, right? And that could go either way. You could either approve them, deny them, or maybe you're going to call them up and say, hey, let's chat and make that human judgment call. Okay. Any questions? That make sense? No? All right. So now, of course, we don't really like this form. It's kind of wonky to say if it's over the threshold, do this, else if it's under the threshold, do that. We want to turn it into a function. And the reason we want to turn it into a function is because when we had our target function, we had a vector instantiation x, and then we output for each one y, where that y value is either approval plus or denial minus. So we want to turn it into a function. Why a function? Because it's easier to evaluate a function than it is to go through all of these conditionals as we see here. Okay. So what we're going to do is let's consider the approval threshold, the approval case, and let's decide to take our weighted sum, I goes from 1 to d, and let's subtract t from both sides of the inequality, okay? So that's our weighted sum, wi, xi, minus our threshold is greater than 0. So now we have our weighted sum minus t, and it's a matter of checking to see if that result is either positive or negative. We can actually code that as a function quite easily. Does that make sense? Any questions? No? All right. So there's a function called sine, not S-I-N-E, trigonometric sine, but S-I-G-N. And what SIGN sine does is if you input a positive value, it'll return positive 1. If you put in a negative value, it'll return negative 1. And I can't remember what it does when you input a 0. Ask Python and it'll tell you. All right. So now, if we take this function, now we can call this function our h of x, hypothesis of x, where x is the vector input. And it's going to either return a 1 if it's an approval for that particular input, that customer vector, or it's a negative 1 if it's a denial. And so for each version of our hypothesis, recall how I talked about our hypothesis set. In the case of slope and y-intercept, each dot represented a slope like minus 0.5 and a y-intercept, say 15. And so here we have a set of weights representing each unique hypothesis. So the first hypothesis is one instance of a line. The next hypothesis is another instance of the line. And so this working hypothesis, h of x, it's a function, but that function is different depending on what our weights are. And those weights for a line on the plane correspond to a choice of slope and y-intercept. Does that make sense? Any questions? Okay. And so D, our dimension is 2 if it's a line on the plane. It's if the dimension is 3, it's a plane in R3 in 3-dimensional space, or it's a hyperplane in arbitrary D dimensions. So we're generalizing what our linear model is. Okay. So now we have a functional form. We have this functional form representing a particular working hypothesis. So let's manipulate this a little bit. Okay. So we want to massage this mathematically a little bit. And we know that we have this minus t in our expression, sine of our weighted sum, wi xi, for each d dimension in our representation. And then we have this minus t. Okay. So now we're going to replace minus t with a constant w naught, w0. And w0 is going to be a real number. It doesn't matter which one it is. Now, of course, we see minus t, real numbers can be negative. So it doesn't matter what it is, we can always represent this minus t, regardless of what its value is, with a real number. And we're just going to name it variable w naught, w0. Likewise, we're going to introduce a dummy variable. We're going to call this x0. And this x0 is going to be fixed to a value of 1, right? Okay. And let's talk about why we do this. So we have our weighted sum. And if we replace minus t with our w naught, the same expression, sine of our weighted sum minus t, is now sine of our weighted sum plus w naught, because w naught absorbs all values of t, including negatives. Does that make sense? Any questions? No? All right. So now that we do that, okay, we'll make another observation. Multiplicative identity is 1. So if we take w naught and we multiply it by 1, that's always equal to w naught. It doesn't change the value. So we can rewrite this w naught as just w naught times our dummy variable x naught, whose value is fixed to 1. Does that make sense? Any questions? All right. So now we'll make another observation. Well, we notice here we have captured underneath our summation with index I goes from 1 to d, and it represents the weighted sum for each one of those terms in our d-dimensional vector. We had a W1, W2, up to WD, and those were the weights for a corresponding first feature, second feature, up to the dth feature, okay? But we have now an additional term here. And you'll notice here the index is 0 for each of these. It's a W naught and we have an X naught. So we can rewrite this expression to include that extra term by just changing our index to 0. Does that make sense? Any questions? Yes. Mm-hmm. 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 Ah, and so in this case, the binary classification, it's similar, but in this case, instead of a one, we say positive one. Instead of a zero, we say negative one. And the reason for that has to do with vector projection. And when you project on a vector, you can tell if it projects on the positive side or on the negative side instead of using zero, one. But zero, one is a different way of thinking about it. Any other questions? No? All right. So we rewrite our expression. It's now sine of this weighted sum for I index goes from 0 to D of Wi times Xi. And it's just a recasting of what we had before by absorbing this constant minus T, our threshold, or like Y-intercept in 2 dimensions, with this little bit of notation change. Does that make sense? Any questions? No? All right. So now this represents a so-called hyperplane in d dimensions. You take your d-dimensional feature vector, you take your d-dimensional weight vector, you augment them. And how you augment them is by including a W naught and including an X naught, where X naught is fixed to 1. Okay. And so now, using vector algebra, we can rewrite this weighted sum as just the W transpose X. If we have our weight vector augmented, consists of W naught, W1, up to and including WD. If we have our X vector, and if you want to make the assumption that they're column vectors, then let me just do that. W is just W naught, W1, WD. And if your X vector represents all of your augmented data, augmented with X naught, so it's X naught, which is fixed to 1, X1, dot, 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 XD. Okay. Now, if you take the so-called vector transpose, you're taking this column and making it into a row, right? And so W transpose is just our W naught, W1, up to WD. So when you multiply vectors together, you go across a row and down a column. Here's X naught, X1, X sub D. And you go across the row, down the column, for the other one you're multiplying, and you just multiply the individual terms together. W naught, X naught, plus W1, X1, plus up to and including WD times XD. And so this W transpose X is also known as vector projection. And what that vector projection does, suppose you have your X vector that way, and you have your W vector plotted there in feature space. What this W transpose X does, it finds the magnitude of the W vector in the direction of the X vector. And so when you do this W transpose X, you're finding this distance, right? It'll give you a value, but it'll also tell you whether it's positive or negative. If it's negative, it means the component of the W vector in the direction of X is in the opposite direction of the X vector. If it's positive, it'll tell you that it's in the same direction as X. So in this case, this example, W transpose X is going to give you a negative value. And in this case, let's say W vector look like this, and X vector look like that. W transpose X is this distance, and it'll be positive because it's in the same direction as X. Okay, does that make sense? So that's a physics-ism. And so the reason why we use +1 and -1 to address your question, Ryan, is that we want to use this idea of vector projection as a function. And so the class labels have to be +1 and -1 for that reason. Okay. Any other questions? Does that make sense? And so this is just a rewriting of this weighted sum using linear algebra, which is not a prerequisite for the class, in order to make it a simpler function. And you can do this inner product, as it's called, in one function, in one function call in something like Python, right? Or MATLAB. And so now we have a closed form functional representation for our working hypothesis evaluated on our input vector x. But in order to compute this W transpose x, it must be the augmented version where we augment with the W naught to absorb that threshold t and the x naught so that the vector is of the same rank as our weight vector. Does that make sense? Any questions? Any questions at all? No? All right. We will have a kind of little crash course on linear algebra, but I was hoping to defer that to the conversation on regression. Okay. So essentially, in vector form, we have the inner product, the sign of the inner product, or the projection of our W vector onto our data vector. And that's going to be our working hypothesis. Okay. And so we haven't talked about the algorithm. And this algorithm is a so-called perceptron learning algorithm. It's actually quite simple, but requires a little bit of machinery about vector algebra and these manipulations. So we start out with some randomization of our initial weight vector, W naught, and we start out with a randomization of our other parts of the weight vector, W1 through WD. So this gives you an initial augmented weight vector, W, right? Likewise, we take our in-sample points and we take the ground truth labels of our in-sample points, our xi, yi pairs, and then we run our first hypothesis, our working hypothesis, over all of our in-sample data, okay? So this is the sign W transpose X, okay? And it's gonna output some Y value, yi hat. And I use hat because it's trying to estimate or guess what the label should be for that particular vector, right? And so either that vector is going to match the ground truth, there's the ground truth, or it's not going to match the ground truth, okay? So we run our working hypothesis, sign W transpose X, over all of our in-sample points, and those points where the working hypothesis disagrees from the ground truth target functions labeling, we're going to call those the misclassified examples. It got it wrong. That's like having the red points on the green side of the line or the green points on the red side of the line. Does that make sense? Okay. So now we look at all of those places where a working hypothesis made an error, and then we're going to pick one of them. Okay. Now, how you pick one, it could be random. That's perfectly fine. Or it could be somewhere in the vicinity of something else that was misclassified before. So now, once you select a misclassified point, you're going to use that misclassified point to drive what the next version of your working hypothesis should be, our next instantiation of the weight vector. And one of the interesting things is not only does it pick the next weight vector for the next working hypothesis, remember, we augmented this with W naught. It's also going to choose a new threshold. What's the appropriate threshold? Does that make sense? All right. So now this is our so-called PLA update rule. The new value of our weight vector is equal to the old value of our weight vector. And remember, our weight vector is augmented, includes W naught, W1 through WD. It's going to be the old value plus the following product. The ground truth label times, and this is a scalar because it's +1 or -1, times the vector that was misclassified. And so in essence, what it's doing, it's saying, I want you to adjust and pick the next hypothesis or decision boundary and make it closer to that instance in feature space that was misclassified. You want to try to move the line so that that misclassified point is now on the appropriate side of the line. Okay. Does that make sense? Any questions? Now, I realize this is not a vector algebra class, so this is the only way I could think of to talk about it. Let's imagine in these two cases, I'll direct your attention to the frame on the left, your left. We have the ground truth class label is +1. So that represents a vector or person who applied for a mortgage who was ground truth approved for the mortgage. Let's imagine this is our vector X in the black going off to the right, and this is our vector W. W transpose X, well, if we project W down to X, it's going to be a -1. So that particular hypothesis, W, at that point in time, is going to say this person should be denied the loan. And that disagrees with the ground truth labeling of +1. So applying this update, we said the new version of W is the old version plus the label times the vector, right? So if we do that calculation, if we add one vector to another, well, y is positive, so it's not going to change the direction of x. And if we add that x to w, that's the same as taking the tail of x and putting it onto the head of w. So now that means the new version of our hypothesis is this weight vector represented by that particular point, this blue arrow. Does that make sense? Any questions? No? And so if we did the W transpose X on this new version, well, wait a minute. It projects on the positive side of this vector. It projects positively. And so it's correcting the labeling. Does that make sense? So it's choosing a hypothesis, said, oh, made a mistake. It's on the wrong side. So change the hypothesis, change the decision boundary so that it now consumes that point so that it's on the correct side of the line. We can do it with the opposite type of error, ground truth, if it were label of -1, okay, that person should be denied a loan. We have our initial W, that's our weight vector. We have our vector X augmented representing that customer. W transpose X, it's on the positive side, so it's going to say +1, and that version of our working hypothesis is going to say this person should be approved. But ground truth, they should be denied. So again, we change that W. How do we change it? W is W plus the label, which is -1, times the vector. So now if we do that, multiplying by -1, it changes the direction of the vector. So X now becomes pointing in the opposite direction. When we do the addition, that's just putting the tail of that negated X onto the head of the W. And this point is our new version representing W plus YI XI. So if we take this new version of our hypothesis, we project that down. Oh, wait a minute. It's on the negative side of the original vector. So it's correcting what that side of the line, that data point should be on. Does that make sense? All right. And so let's go to a different picture. And when we do this update, what I showed you before is called the hard update. And you never update with a hard update because it abruptly changes the position of the decision boundary in a way that you can damage the correction that you've made to the hypothesis for other points. And so typically what happens is you modulate the size of the update with a parameter eta. And eta is usually between 0 and 1. And it says when it's 1, do the full update. But typically it's about 0.1 plus or minus depending on your data set. And this is called a learning rate. And it says this is how dramatically you should let this misclassified point influence how the decision boundary moves. Does that make sense? Any questions? No? All right. So now another way of thinking about it, oh, and I have my daughter with me here today because it's April vacation, but another way of thinking about it is if each point is a type of magnetic particle, in our decision boundary, the line is a piece of metal, right? That's attracted by those little magnetic particles. You can think of this perceptron update rule as moving the boundary. It's like it's attracted to these points that are misclassified. And in that case, here we have our working hypothesis, say at time step 0, H at time step 0, and it has a particular version of a weight vector. And then when you apply the PLA update rule, maybe this point here, it's misclassified. It's a positive point, should be approved, but it's on the negative side of the line. It moves the decision boundary by selecting a new hypothesis. And I'll try to draw a straight line here for the new position of the hypothesis. And when it does that, this point that was misclassified now at the next instant is now positively classified. But you'll notice I moved it so much, this point that was correctly classified is now misclassified for the new position of the decision boundary. So this learning rate eta says don't move it that dramatically, only move it a little bit in that direction. Does that make sense? Any questions? All right. And so this decision boundary or partitioning line for feature space, it moves or changes as a result of the PLA update rule. And this learning rate tells you how much it's going to move because we want to move it in the direction, but not completely influenced by each misclassified point. Okay. And so you keep doing this for some number of rounds, and really that's it. Perceptron learning algorithm. This is the linear case, and there are lots of tools like kernels and nonlinear mappings that you can use to transform this linear model for free to get the power of a nonlinear decision boundary. And that's outside of the scope of our discussion for this class. But there are lots and lots of issues wrapped up in this. How many rounds do you run this? What does convergence mean? Maybe convergence means the error rate in sample error changes no more than 5% from one round to the next. Maybe it's a fixed number of rounds, like 1,000 rounds or 100,000 rounds. That's one of the things that you need to talk about. Will it work for any problem? What sort of geometries for your point clouds will this work well for? Because it doesn't work well for all geometries. Do you change the family of functions or do you change the way you're searching? How do you choose the hypothesis set? If the hypothesis set is too big, like degree million polynomials, then you're going to need much more data to pay for those extra parameters. And that's outside of the scope of this class, one of those physics of learning. How do you choose the algorithm? How do you choose the method you use for searching? And there are all sorts of variations for that. And how much data do you need? There's a direct exponential relationship between the dimensionality of your model and the amount of data that you need if you want generalization to work well. And there's a rigorous set of theoretical proofs for that based on something called Hoeffding's inequality. All right. Any questions? All right. So that would be the subject of a machine learning course. All right. So that's all I had for perceptual learning algorithm, and that completes our machine learning high level. Let's jump right into unsupervised learning. I'll just motivate that for the next probably 7 minutes or so for clustering. Okay. So let me share screen. Let me mute that. Let me share screen. First, let me bring up the PowerPoint. Kill the PowerPoint. And slideshow. Save, exit. So let me bring up the next one on clustering. Open. That was 24. Share. Did that come up? No. Escape. So let me reshare the screen. 24. There we go. Share. Let me slideshow. Let me unmute. It's the wrong version on my screen. It's different there. Check. All right. Still up. And that should be up. All right. So let me go back to that. I think we're okay. All right. So let's jump right into clustering. And so our final exam is going to be Friday, the 5th of May, 10:30 to 12:30. This is the first time in my 2 years here that I've had an exam that wasn't at 8 o'clock in the morning. So I'm happy about that. After today, of course, 2 weeks left. We talked about anatomy of a learner. We talked about regularization sequence. We talked about perceptron update rule and the idea of a decision boundary as being what's called an attractive field, magnetic attraction to for metal boundary. So we talked about unsupervised learning only at a high level. And we said that if you don't have access to ground truth labels, the best you can do is look at the data itself, look at the features. And so this is best described by this idea of birds of a feather flock together, right? And so of a feather means that we're looking at the values of the features. Because, for example, if two mortgage applications, let's say one had annual salary of 70,000 and the other had an annual salary of 71,000, they're very close by one another. They're very similar in terms of feature space. So we can use this idea of similarity to analyze which data examples are in the same group in terms of their behavior, what these features are. And so I'm going to motivate this idea of features and grouping using an example from computer vision. And we'll be teaching a computer vision course in the fall. I highly encourage you to take it. But if you were to look at this image, how would you describe the differences between these images based on the content, the data itself, right? If you didn't know that this was a building and this was a field of sunflowers, how would you describe it? Not a trick question. How could you describe it? You ever thought about that? If you did not, now I know you know what they are, right? But it's kind of hard to kind of unlearn what you already know, right? How would you describe it? What could you use? What do you think? Colors, you could use colors. So tell me about some of the colors on the left. It's very white, okay. Anything else? You see a white for building. The blue sky, good. Blue sky. Anything else? Some green, okay. Green for the shrubbery and stuff like that. We have the road too, okay. What about on the right? What do you see there? Yellows, okay. Anything else? We see blue and green. Now, we have green on the left and green on the right. Is it the same green? No, it's a different green. Okay. We also see shapes. We see lines. Now, for human engineered structures, the lines tend to be orthogonal. We have vertical lines. We have horizontal lines. Maybe they're a little bit slanted, but they're for the most part horizontal lines and vertical lines. Okay. For the sunflowers, we see curves, right? Natural things tend to be curves. If you ever see a square tree, run, something's wrong, right? We see curves. And so if you think about what a curve is, we have, if you trace the edge of a curve, you have lines, and these lines are at different angles from 0 to 180, okay? So we see a different set of lines, and we see different sets of colors. And so if, and this is a subject of computer vision, you were to characterize the content of these images, you'd need a representation of the distribution of the colors and the distribution of the lines. And lines are the descriptors of shape, right? Okay, so let's talk about color. Now, when you talk about color, you represent color as a mixture of components. And I'm going to talk about the RGB, red, green, blue color space. There are many others, but we're only going to focus on RGB. Now, this is the so-called RGB color cube. And what this represents, you have three axes. One is the red axis, so there's red. One is the green axis, and one is the blue axis. Each position in this cube represents some mixture of red, green, and blue. And the color of each little cell or block or sugar cube, if you will, carved out of it is the color represented by that mixture of red, green, and blue. One of the other things you'll notice about this RGB color cube is we have this line here coming from the origin of RGB color cube or color space, and it goes all the way out. Forgot I was on a new slide. It goes all the way out, use black, start the origin, and it goes all the way out to the extreme position in this representation. That's called the grayscale line. And a gray is an equal mixture of parts red, parts green, and parts blue. Now, computationally, how you represent it is 256 different levels from 0 to 255 of the red component, the green component, and the blue component. Does that make sense? Okay. And so each one of these mixtures represents a unique color. So I'll end with this. Let's kind of test this out. Wholeness, I don't believe you. Okay, that's valid. Don't ask me. Let's test this out. And so in a browser, basic HTML, I know this is old school, but humor me. When you want to set the background color for a web page, you say BG color equals, and you have hexadecimal digits. A hexadecimal digit is base 16, and base 16 goes from 0 to 9 for 0 to 9. And then you say for 10, it's A, B, C, D, E, and F. So that's 0 through 9. This is 10, 11, 12, 13, 14, 15. And because it's base 16, each hexadecimal digit is one of these characters 0 through F. Okay? Now, when you set the background color, you have 8 bits to define the red, 8 bits to define the green, 8 bits to define the blue, RGB. And so F here is 255, which is all ones. 1111, that's 15, 1111. And so each one of these, this represents 8 bits, it's 2 hex digits, it's 4 bits each to represent from 0 to 15. So this says, give me all 255 saturation level for the red component of the mixture. And so with this, you can actually, with specificity, control the background color among all the different mixtures that you can have using RGB. And so don't believe me, and I hope you don't. Let's try this out in HTML, okay? So let me bring up here, and let me change the share. Share screen. Let me do that. Where's Firefox? Firefox, there. Okay, share. All right, so let me bring up, I already kind of have the file open, and let me go to my editor session here. And you notice I say FF, FF, FF. So that's 255 maximum saturation of red, maximum saturation of green, maximum saturation of blue, right? That's going to be white, okay? So let me go to the browser window, shift reload, and you notice, oh yeah, it is white. That's that extreme point on the grayscale line. So let me turn off the green and the blue. So it's full saturation of red. Let me say green is 0, 0, and blue 0, 0. Okay. So let's make this full red. So let's see what we get. And you'll notice it's full red, right? It's pretty loud red. It looks really, if it looks bright on that screen, it looks really bright on this screen. So let's try something in the middle. Let's say F, not really in the middle. Let's say 15, it's about 7. So 7F, right? It's about halfway for the red. Let's see what happens here. And you notice it's a darker red, right? It's less saturated than full saturation red. Okay, this is interesting. So let's turn off the red component, 0, 0, and let's turn on the green, FF. So we have 0 saturation red, full 255 saturation green, 0 saturation blue. So we'll save that. We'll reload the browser. Oh, wait a minute. It's a pretty loud green, very bright. You can see the reflection on the back wall. This is funny. So we can try this green. Let's make that 7F, which is about halfway in the saturation, like 120, 126 or so. Let's save that and let's reload. And our green is a little bit deeper. Likewise, we can do the same thing with blue, 0, 0, FF, and I won't do the halfway for blue in the interest of time. So it's full saturation of blue, everything else is 0. And we have our deepest blue. Let's test out the grayscale. We said grayscale is equal parts red, green, and blue. We showed you what white is. So let's do 7F for the red. Let's do 7F for green, and then lastly 7F for blue. We'll save that. We'll reload and end with that. And reload, you'll notice it's gray. If we take it and maybe we'll make it 2F, right? We make it a deeper gray. It'll start to look black. 2F and 2F. Okay, we'll save that. And we reload. Well, that's like a mid-gray. And you notice it's a darker gray, right? And so this is just to say, computationally, when you look at a color representation, it's a mixture of red, green, and blue. And we have 8 bits to represent the saturation of red, 8 bits to represent the saturation of green, and 8 bits to represent the saturation of blue. And don't ask me what these colors are. My crayon box only had 8, so I only know primary colors. I can't tell you sunflower versus yellow versus butter. It's just all yellow to me. All right. So with that, we'll end there. It's time. And we'll pick back up on Wednesday with more on clustering and hopefully get a chance to use the Python APIs. I'll see you all on Wednesday. Have a great week.